Can you hear me?
Yes.
Okay, sorry about that.
Oh, no worries. I just didn't make sure that your house didn't get hit by a UFO or something.
Oh, not yet. No, I have this thing where my window sleeps if I haven't done anything for a while. I can actually disable that. Never suspend this site. Okay, I could turn the stream back on. Was that are are you having any luck implementing that algorithm? Should we try to um, pair program it or anything?
Um,
Do you want to mess with it or
Not really.
okay? We just not mess with it because I mean I think we
Yeah,
could just talk through it.
yeah, because I think that's what it would probably be worthwhile to study that, but I think to actually like do it properly probably takes is like to actually do it live is maybe not the best delivery mechanism for that sort of thing, you know?
Yeah, yeah, totally. Um, yeah, maybe I'll give myself that as homework,
Yeah.
and then it'll be interesting because I'm gonna have to do it. I don't know any other way than to just use like several nested if if conditions
Yeah.
and loops. Well, just using not loops, using recursion, and then just
Right.
having like an accumulator
Yeah.
and maybe some kind of boolean just to check. It's like, do we have three yet? If we don't have three, then call yourself again,
Right.
increment the accumulator. Once it's
Yeah.
three, then go on to the next,
Yeah.
etc. Yep. That kind of thing.
Totally.
All right. Well, let's just keep reading. If that sounds
Let's.
good. Okay.
Sure.
There's another exercise and then another exercise.
Yeah, let's skip the exercise.
Let's
This
just
is
skip all that. Yeah.
yeah.
Okay. Notes. Do you feel like reading the notes?
I can.
You want to?
Sure. Okay.
It
So
starts with
yeah. Oh, we got a footnote. Woohoo! Okay, so
oh, I guess these are all. Oh, these are just the footnotes. Never mind.
oh, okay. So
So we finished.
oh yeah, yeah. Okay, so yeah, we're done.
Woohoo!
Yay!
Yay. I'll just go. I'll just go back later and actually do that stuff. Yeah.
Great. Okay.
Yeah.
So
Maybe we
do you
should
want to
have.
dive into?
Oh, sure.
Sorry. Go ahead.
Maybe we should have something like later on if we get kind of or maybe like start next week or something or the next time we do this,
Mm-hmm.
we could have
Mm-hmm.
like a quick kind of like blast through the material and then have like a recitation
Yeah, like,
at
or
the
to do like
end.
kind of a recap and
Yeah.
go over this stuff that we skipped. So
Yeah, or maybe do the exercises and then start off with them the next week. Just like here were my
yeah,
answers.
yeah, I like that idea.
Okay, cool. Yeah, we'll do that then. Okay, so 1.3.
Yep.
Okay. I don't mind reading because I feel like
Okay. No. I can read. It's fine. Um,
you read so much more than me though.
do I?
Oh, just in
I don't
life.
think. Well, but that's because in part I get paid to. So, um, but
Well, there.
uh, I've actually I don't know. It might be interesting. I don't know if I talk more than you, and I go more off the cuff than you do because I bring my background into it. But anyway,
Yeah,
so
I'm pretty talkative.
yeah. Um, Formulating abstractions with higher order procedures. We've seen that procedures are, in effect, abstractions that describe compound operations on numbers independent of the particular numbers. For example, when we define cube of x as x times x times x, we are not talking about the cube of a particular number, but rather about a method for obtaining the cube of any number. Of course, we could get along without ever defining this procedure by always writing expressions such as 3 times 2 times 3, x times x times x, y times y times y, etc., etc., and never mentioning cube explicitly. This would place us at a serious disadvantage, forcing us to work always at the level of the particular operations that happen to be primitives in the language, multiplication in this case, rather than in terms of higher level operations. Our programs would be able to compute cubes, but our language would lack the ability to express the concept of cubing. One of the things we should demand from a powerful programming language is the ability to build abstractions by assigning names to common patterns and then to work in terms of the abstractions directly. Procedures provide this ability. This is why all but the most primitive programming languages include mechanisms for defining procedures. Yet, even in numerical processing, we will be severely limited in our ability to create abstractions if we are restricted to procedures whose parameters must be numbers. Often, the same programming pattern will be used with a number of different procedures. To express such patterns as concepts, we will need to construct procedures that can accept procedures as arguments or return procedures as values. Procedures that manipulate procedures are called higher order procedures. This section shows how higher order procedures can serve as powerful abstraction mechanisms, vastly increasing the expressive power of our language. Procedures as arguments. Consider the following 3 procedures. The first computes the sum of the integers from a through b. Define some integers a, b. If a is greater than b, return 0. Otherwise, add a to the sum of integers a plus 1 and b. The second computes the sum of the cubes of the integers in the given range. Define some cubes a, b. If a is greater than b, return 0. Otherwise, add the cube of a to the sum of cubes of a plus 1 and b. The third computes the sum of a sequence of terms in the series 1 over 1 times 3 plus 1 over 5 times 7 plus 1 over 9 times 11, so on and so on, which converges to pi over 8 very slowly. And then footnote, this series, usually written in the equivalent form, pi over 4 equals 1 minus 1/3 plus 1/5 minus 1/7, so on, is due to Leibniz. We'll see how to use this as the basis for some fancy numerical tricks in section 3.5.3.
Yeah.
Yeah.
Did you ever see, quick tangent, did you ever see that movie, The Man Who Knew Infinity?
I don't think so.
It's pretty good. It came out a couple years ago. It was about Patanjali? Oh, no, not Patanjali. It was about one of the discoverers of that kind of, that like the sum of all numbers somehow equates to like negative 1/12. I forget.
Okay.
Like one of these.
Okay, interesting. Here we go. The story of the life and academic career of the pioneer Indian mathematician Srinivasa Ramanujan?
Ramanujan.
Okay, I was going to say I'm probably putting the emphasis on the wrong syllable or something like that. But
yeah.
Is that Dev Patel playing him?
It is.
He's everywhere. Okay, he's in everything these days.
He is.
Which good for him. He's a decent actor. So
yeah,
why not?
Jeremy Irons is quite good in it.
Yeah. Oh, he's in it as well. Okay. Cool.
It's pretty good. It's worth watching.
Okay, let's see if it's on like Netflix or Amazon Prime or whatever.
Should be.
Cool. Anyway, where were we? Okay. Here we go. No. That's cool. So the scheme implementation, what we just talked about, define pi sum a b if a is greater than b, return 0. Otherwise, add 1 divided by, and then that whole sum thing. A times a plus 2, a plus 4, and all that good stuff, plus b. So these three procedures clearly share a common underlying pattern. They are, for the most part, identical, differing only in the name of the procedure, the function of a used to compute the term to be added, and the function that provides the next value of a. We could generate each of the procedures by filling in slots in the same template. Define name AB if a is greater than b, return 0, otherwise plus term a, and then name next a, b. The presence of such a common pattern is strong evidence that there is a useful abstraction waiting to be brought to the surface. Indeed, mathematicians long ago identified the abstraction of summation of a series and invented sigma notation. For example, n equals a up to b, f of n equals f of a, so on and so on, plus all the way up to f of b to express this concept. The power of sigma notation is that it allows mathematicians to deal with the concept of summation itself rather than only with particular sums. For example, to formulate general results about sums that are independent of the particular series being summed. Similarly, as program designers, we would like our language to be powerful enough so that we can write a procedure that expresses the concept of summation itself rather than only procedures that compute particular sums. We can do so readily in our procedural language by taking the common template shown above and transforming the slots into formal parameters. Define sum term a next b. If a is greater than b, return 0, otherwise plus term a, sum term next a, next b. Notice that sum takes as its arguments the lower and upper bounds a and b together with the procedures term and next. We can use sum just as we would any procedure. For example, we can use it along with a procedure inc that increments its argument by 1 to define sum cubes. Define inc1 as n plus 1. And then define sum cubes AB as sum cube A inc B. Using this, we can compute the sum of the cubes of the integers from 1 to 10, sum cubes 110, and it gives you 3025. With the aid of an identity procedure to compute the term, we can define some integers in terms of sum. Define identity x, x, define some integers a, b, some identity a inc b. Then we can add up the integers from 1 to 10, some integers 1 to 10, and that is 55. We can also define pi sum in the same way, and we have another footnote. Notice that we have used block structure, section 1.1.8, to embed the definitions of pi next and pi term within pi sum, since these procedures are unlikely to be useful for any other purpose. We will see how to get rid of them altogether in section 1.3.2. And so define pi sum AB, define pi term x as that whole thing, and then define pi next as the formula for the next in the series, and then sum pi term A, pi next B. Using these procedures, we can compute an approximation to pi, times 8, pi sum 1/1000, and lo and behold, we have 3.1395926, blah, 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 which is pi-ish.
Not unlike pi.
Yeah. So it's like a pot pie, maybe.
It's a pot pie.
There we go. Okay, anyway, once we have sum, we can use it as a building block in formulating further concepts. For instance, the definite integral of a function f between the limits of a and b can be approximated mathematically using the formula. The integral from a to b of f equals f of a plus dx over 2 plus f of a plus dx over 2 plus f of a plus 2dx plus dx over 2, and so on and so on and so on, dx for small values of dx. We can express this directly as a procedure. Define integral f a b dx. Define add dx x plus x dx times the sum of f a plus a divided by dx over, or say, wait, a a plus dx over 2, add dx, b, dx. Yeah. Integral, so it gives an example here, integral cube 0, 1, then 0.01, and it gives 0.2499, et cetera, et cetera, et cetera. I'll take their word for it. And then integral cube 0, 1, 0.001, and it gives another very similar value. Here we go. The exact value of the integral of cube between 0 and 1 is 1/4. Good to know.
So the floating, that's where we get into some of the the precision floating point
Right.
kind of issues.
Yeah. Well, and dx is basically like an error tolerance.
Okay. Oh, interesting. Okay.
So notice with the smaller value of dx, the 9s went out a little bit further.
Yeah.
So.
Okay.
Busting 5 9s win, whipping out my coat. Sorry.
Ooh, if you make the dx, if you put too many zeros, it quickly breaks.
I would imagine it would.
Yeah.
Did you just try it and ripple it?
Yeah, I just tried
Okay.
001 or 0001.
Oh, okay. Just adding 2 more zeros, that broke it, huh?
Just one more zero.
Oh, just 1 more zero. Oh, okay.
For the last one. Yeah.
Okay, well, there you go.
1/10,000th.
Okay. Well, there you have it. So, okay, I'm not going to go over these exercises. I'm feeling lazy.
Yeah.
And what this is all building up to anyway is the headline of section 1.3.2, constructing procedures using Lambda.
Yep. There it is.
Yeah, you knew this was coming, right?
I felt it. I felt it sneaking up.
Yeah, there was a little bit of foreshadowing. It was like Chekhov's Lambda function.
Yeah. Indeed. There's also kind of some currying nearby.
Yeah. That'll come up as well, I'm sure. So.
Yeah.
Okay, so in using sum as in section 1.3.1, it seems terribly awkward to have to define trivial procedures such as PyTerm and PyNext just so we can use them as arguments to our higher order procedure. Rather than define PyNext and PyTerm, it would be more convenient to have a way to directly specify the procedure that returns its input incremented by 4 and the procedure that returns the reciprocal of its input times its input plus 2. We can do this by introducing the special form lambda, which creates procedures. Using lambda, we can describe what we want as lambda x plus 4, and it returns the same thing, or lambda x 1 divided by x times x plus 2. Then our PySum procedure can be expressed without defining any auxiliary procedures as define PySum AB sum lambda x 1 divided by x times x plus 2 a, and then lambda x plus 4 b. Again, using lambda, we can write the integral procedure without having to define the auxiliary procedure add dx. Define integral f a b dx, then multiply the sum of f, and then add a plus dx over 2, lambda x plus dx, and b, and then multiply that by dx at the end. In general, lambda is used to create procedures in the same way as define, except that no name is specified for the procedure. So it's just lambda, formal parameters, body. So an anonymous function, basically. The resulting procedure is just as much a procedure as one that is created using define. The only difference is that it has not been associated with any name in the environment. In fact, define plus 4x is x plus 4 is equivalent to define plus 4 lambda x plus 4. We can read a lambda expression as follows. Lambda, the procedure, x of an argument x, and then plus x4, that adds x and 4. Fairly self-explanatory. Like any expression that has a procedure as its value, a lambda expression can be used as the operator in a combination such as lambda xyz plus xy square z 1, 2, 3. And that gives you the result of 12. Or more generally, in any context where we would normally use a procedure name. And we have a footnote. It would be clearer and less intimidating to people learning Lisp if a name more obvious than lambda, such as make procedure, were used. But the convention is firmly entrenched. The notation is adopted from the lambda calculus, a mathematical formalism, there we go, introduced by the mathematical logician Alonzo Church, 1941. Church developed the lambda calculus to provide a rigorous foundation for studying the notions of function and function application. The lambda calculus has become a basic tool for mathematical investigations of the semantics of programming languages. Okay, so using let to create local variables. Another use of lambda is in creating local variables. We often need local variables in our procedures other than those that have been bound as formal parameters. For example, suppose we wish to compute the function f of x and y equals x times 1 plus xy squared plus y times 1 minus y plus 1 plus xy times 1 minus y, which we could also express as a equals 1 plus xy, b equals 1 minus y, f of x and y equals xa squared plus yb plus ab. In writing a procedure to compute f, we would like to include as local variables not only x and y, but the names of intermediate quantities like a and b.
Oh, strange. It dropped me.
Oh, sorry. In writing a procedure to compute f, we would like to include as local variables not only x and y, but also the names of intermediate quantities like a and b. One way to accomplish this is to use an auxiliary procedure to bind the local variables. So define xy and then define f helper ab plus add x times square of a times yb times ab, and then f helper 1 plus x times y, or you pass 1 plus x times y, and then 1 minus y as your parameters. So, of course, we could use a lambda expression to specify an anonymous procedure for binding our local variables. The body of f then becomes a single call to that procedure. Define f of x and y, lambda ab plus times x square a times yb times ab, and then plus 1 times xy, and then minus 1y. This construct is so useful that there's a special form called let to make its use more convenient. Using let, the f procedure can be written as define fxy, let a be 1 plus x times y, and b be 1 minus y, and then plus x times square of a, and then times yb, and then times ab.
Yeah.
So the general form of a let expression is let var1 equal expression 1, var2 equal expression 2, and so on and so on and so on. Var(n) equal exp n, which can be thought of as saying let var1 have the value exp1 and var2 have the value exp2, and so on and so on. Var(n) have the value exp n in body. The first part of the let expression is a list of name expression pairs. When the let is evaluated, each name is associated with the value of the corresponding expression. The body of the let is evaluated with these names bound as local variables. The way this happens is that the let expression is interpreted as an alternate syntax for lambda, var1, so on and so on, through var(n), body, expression 1, so on and so on, through expression n. No new mechanism is required in the interpreter in order to provide local variables. A let expression is simply syntactic sugar for the underlying lambda application. We can see from this equivalence that the scope of a variable specified by a let expression is the body of the let. This implies that let allows one to bind variables as locally as possible to where they are to be used. For example, if the value of x is 5, the value of the expression plus let x3 plus x times x10, and x is 38. Here, the x in the body of the let is 3, so the value of the let expression is 33. On the other hand, the x that is the second argument to the outermost plus is still 5. So the variable's values are computed outside the let. This matters when the expressions that provide the values for the local variables depend on variables having the same names as the local variables themselves. For example, if the value of x is 2, then let x3, y plus x plus 2, and then times xy will have the value 12, because inside the body of the let, x will be 3 and y will be 4, which is the outer x plus 2. Sometimes we can use internal definitions to get the same effect as with let. For example, we could have defined the procedure f above as define xy, and then define a as 1 plus x times y, define b as 1 minus y, and then add x to the square of a, add x times the square of a, y times b, and a times b. We prefer, however, to use let in situations like this and to use internal define only for internal procedures. Then footnote, understanding internal definitions well enough to be sure a program means what we intend it to mean requires a more elaborate model of the evaluation process than we have presented in this chapter. The subtleties do not arise with internal definitions of procedures, however. We will return to this issue in section 4.1.6 after we learn more about evaluation. You remember when we were talking about like free variables versus bound variables, and you were saying you were trying to think of it as a global versus local thing, and I said that's really not the way to think of it. This is why. This is what I was trying to get at in that discussion.
Okay. Cool.
Because even once you introduce functions like this, local becomes kind of a relative term.
Right. Free variables.
Does that make sense?
Yes. Do you want to stop right there?
I think that's a good. I think that's a good stopping point.
Yeah, and that's also a lot of material for me at least, to try to look over this week.
Oh, it is for me too.
Cool. Well, maybe maybe beginning of next week, or maybe over the weekend, I'll send you a ping and just see how things are going.
Okay, sounds good.
Okay. Yeah, I think we should get some rest.
I think we should too. That sounds like a smashing idea.
Okay. Well, thanks as always. This was great. Thank you for your insight and reading. Very enjoyable.
Okay, thank you for organizing all this.
Oh yeah. That's all.
Alrighty.
Well, have a great night.
Good night, Scheme Land.
Yeah. Goodbye, Scheme. Good night, Danielle. I'll see you later.
Good night. All right.
Bye.